Hello WeatherTech students, and today we're going to go on to our next week's lecture. Here we're going to talk a little bit about vorticity, talk about thickness, and talk about how we can horizontally transport a number of properties, and we refer to this as advection. And so as you can see on the screen, here's the join code for Adam's lecture, 602987. If you wish to join Kevin's top hat at some point, it's 393390. Again, there's no reason to have to look at the slides in a synchronous fashion here, but simply if you wish to access them at a later time. And so as we start our presentation here, you can see the topic slide, thickness, vorticity, and advection. And this will be relatively short, and I highly encourage you to spend a little additional time with a handout gaining comfort on these parameters, which are going to continue to evolve over the course of your meteorological career at Valparaiso University. And so when we start with this idea of atmospheric thickness, we've mentioned thickness on occasion back in Met 103. We've talked about thickness in terms of whether it's going to be rainy, whether or not it's going to snow, whether or not it might be that freezing rain or even sleet. And so when we talk about thickness from a generic standpoint, we're simply referring to the difference between two atmospheric levels, this distance, say, between the surface and 300 millibars. Not that that may be of much use to us, but we're going to look at what's that relationship between two levels of the atmosphere, remembering that we usually refer to these levels in terms of heights. What is the height at 500 millibars, so on and so forth. And this is going to be related in many ways to your ideal gas law, your P equals rho RT. And so we will look at a number of different thicknesses. 1,000 to 500 millibars is a very common one to look at. It used to be something that was utilized almost exclusively to try and delineate the difference between rain and frozen precipitation. But we've learned over the years that looking primarily at the lower levels of the atmosphere is going to be critical in determining what type of precipitation one might expect. And so other thicknesses, say surface to 850 millibars, is a little more commonly used to really get a idea of what the temperature profile is in the lower portion of the atmosphere. Remembering 850 millibars is usually at about 1.5 kilometers. But in fairness, you can make your own up. It's one of those things that we can talk about a thickness between any two layers of the atmosphere. But what's important to know is that the higher the thickness, the higher the temperature in the higher the average temperature within that layer that you have chosen to calculate a thickness from. And so here again, directly proportional to the idea of virtual temperature. We'll talk more about virtual temperature later on in your thermodynamics curriculum, though you'll touch upon it a little bit more in 216. It involves including parameters such as moisture within your temperature calculation. And so why do we care about thickness? Here we're looking at simply the fact that warm layers are going to be thicker than your cold layers. We know that warm air is going to choose to expand over the course of time, and so this warm layer, if we have warmer temperatures, is going to be thicker. So as we work our way into summer and thinking of, say, under a nice strong ridge in summertime, we may have a very high value for your 1,000 to 500 millibar thickness. And as you work your way into the colder months, in the wake of a trough, we may see lower thickness values. Again, cold air more dense than warm air. And the main reason we care again is that we're going to look at this in terms of what could happen in terms of precipitation. And so this is just a quick snapshot of some of the thicknesses going on here Thursday afternoon. This is taken from the Storm Prediction Center. And so one thing that a number of different entities will put out is a product looking at what's known as critical thickness values. And so if you look at the key at the bottom, you'll notice that we have 4 lines here, and they're all going to correspond to a different thickness. So your red line there, which has 5,400 on it, is going to be your 1,000 to 500 millibar thickness. The 2840 green line is 1,000 to 700 millibar thickness. Your 1300 blue line is your 1,000 to 850 millibar thickness. And then finally an 850 to 700 millibar thickness in terms of yellow. And so one of the things that's very important here is that the deeper the layer of the atmosphere that we're looking at when we calculate thickness, the more we have to try to interpret where different temperature layers might be. And so let's focus for a moment on the 1300 thickness line there. This is again looking at values that are going to be north of this, that are going to have lower thickness values than 1300, and down here across much of South Dakota, southern Minnesota, and the Great Plains, we're going to have 1850 millibar thicknesses that are greater than 1300. And so this may be one product that folks are going to look at and trying to determine whether or not we might expect more snow up in areas, say, such as northern Minnesota if there were precip, versus primarily rain. And so it is highly likely at some point in your career you'll hear something about the 540 line, and this is your 5400 millibar thickness. Again, for many years this was focused on very strongly in the idea that thickness is lower than 5400. We would be looking more at a snow profile versus a rain profile in areas with thicknesses greater than 5400. Moving forward into vorticity. Vorticity we've brought up on occasion already in MET 130, and when we talk about vorticity, simply put, we're talking about spin in the atmosphere. And so we're going to parse this out a little bit here into two different types, relative vorticity and Earth's vorticity. In fairness, we'll also talk about absolute vorticity. Absolute vorticity simply being a sum of relative and Earth's vorticity. And so what do we mean when we talk about relative and Earth's vorticity, the spin in the atmosphere? Relative vorticity is going to be related to the change in wind components over a given distance. And so we have an equation here, delta V over delta X minus delta U over delta Y. And so if we broke down our wind into U and V components, and we looked at both distances on a grid in the X and Y direction, we would be able to plug and chug some values in here for all the deltas. Again, delta signifying a change over a given time or distance. And here we're simply going to do the calculation to determine what your relative vorticity is. And so if we have large changes in wind over a small distance in certain ways, we're going to have higher values of relative vorticity. Earth's vorticity is in many ways simpler, but it's not going to necessarily tell us as much about what's going on with troughs and ridges in the atmosphere, because it's simply related to latitude and the Coriolis parameter. And so you'll see what will become very familiar equation as you work out over time, 2 omega sine phi, with phi being your latitude. And so we have high values of Earth's vorticity near the poles, low values of Earth's vorticity as you move towards the equatorial region. And so again, this is not going to have any significant, it's not going to be influenced, I should say, by whatever weather patterns are going on. That's going to be more the relative vorticity. And so absolute vorticity, we're oftentimes going to be focusing on those changes that are influenced by the relative vorticity component of the equation. Why do we care about vorticity? It's nice that the Earth spins. It's nice that there's additional spin going on in the atmosphere due to our weather systems. But this is going to help us in the short term really be able to identify where we have some troughs and ridges. And we'll have some examples, especially in an upcoming video that looks at some of these current weather that's going on in terms of vorticity thickness as well as advections. This is going to become increasingly important as you move into the sophomore and especially the junior curriculum, when we start to utilize vorticity to help determine areas that we may expect to see rising motion and therefore precipitation, or where we might find sinking motion primarily. And so this map from a few years ago shows 500 millibar absolute vorticity, again combining those two parameters. We'll talk a little bit more about this when we get into the Pythonic portion of the lecture, but we're going to have very small values of spin, and so we're going to have to scale those in order to have them show up on a map. And so here at the bottom you can see the scale. We work our way from slightly negative values all the way up to values in the 30 and 40 range. And so here you can see our heights at a low value. We have a closed contour here. Again, we're going to primarily look at things up at 500 millibars when we look at vorticity. And you can see some high values spinning around this area, this trough across the midsection of the country. Some very high values here near the Red River Valley. And then, as we're going to talk about shortly, we often concern ourselves much more with the idea of vorticity advection. In other words, where is the wind, which here would be rotating counterclockwise with this trough across the plains. Where is this wind? For instance, moving kind of a west-southwesterly direction across northern Texas, moving these high values of vorticity to. And so let's call this Wichita Falls, our little bullseye here on this model plot. We would have some cyclonic vorticity advection across much of eastern Oklahoma. Areas of higher absolute vorticity being advected into areas of lower vorticity. And again, we'll spend a little more time about that on the subsequent video. But one thing you should note here is, where do we see some of our high values of vorticity? Here absolute, but again, focusing on the idea that much of the changes are a product of these differences in relative vorticity. Well, your highest values are, not surprisingly, right around this deep trough feature across the plains. You can see some other high values here up across the provinces of Canada, again in association with the trough. You can see a spin out here off the eastern Canadian coast, again some higher values of vorticity, and then areas where we see ridging, relatively small vorticity in this broad ridge across much of the Midwest down into the southeastern United States. And so we'll conclude this lecture series here talking about advection. And when we talk about advection, it's simply a fancy term for taking a variable and considering how it is being transported horizontally. And so here at the title, you'll see I talk about temperature advection, vorticity advection. You can derive other types of advection, but we're going to look primarily at those two types of advection here. And so temperature advection, we're simply referring to it as warm air advection or cold air advection. And here we're not necessarily concerning ourselves with diurnal heating. In other words, is it going to be warm this afternoon? Maybe the sun's out where you live. There's some rain here in Valparaiso as I am recording this video, but you might get some intense heating over the course of the day and therefore warm up. However, there are also days where we get very little solar insolation, but it still warms up significantly into the afternoon hours. And that is often due to warm air advection. The idea that the wind, or the horizontal wind to be specific, is helping to move areas that are warmer into areas that were colder. Think about a warm frontal boundary. If we're moving air from here, the south, towards the north into Indiana, Ohio, Michigan, or wherever you may be located right now, we may see warm air advection near that warm frontal boundary. Conversely, when the cold front comes through and we bring some of that cold continental polar air into an area that was just in the warm sector of a cyclone, we may experience very rough, harsh, cold air advection as that works its way in. Considering vorticity advection, we're going to look at vorticity advection and the idea of being cyclonic or anticyclonic. You'll oftentimes see these abbreviated as CVA and AVA respectively. And so here again, we're going to focus, at least for the purposes of MET 130, on 500 millibar vorticity and vorticity advection. Is the flow at 500 millibars, which is going to be either some form of geostrophic or gradient balance because we're above the frictional air, is it advecting vorticity in a way that increases or decreases the local spin? And so this is going to have a large bearing on where we have high or low values of vorticity, how are they oriented relative to the wind? And so in this schematic down at the bottom, here we are looking at some temperature advection. You may consider whether or not your temperature lines, your isotherms, how are they located or how are they oriented relative to your height lines or at your surface, your isobars. And here we can see a strong cross flow, again this wind that would be blowing cold air into areas of warm air, and so this would be a cold air advection type scenario that we would be looking at here. However, if your isotherms and heights are located in a relative parallel sense, here we may have the wind blowing very similarly, but we're not actually moving different values of temperature into a different type. Again, that probably wasn't phrased the best, but the idea that here we would simply be moving temperatures near 5 degrees into areas that are 5 degrees. And so this would be a scenario in which we would not be getting any significant advection of temperature, and we can do this in a similar fashion to understand vorticity. And so here we'll conclude with looking at a map here. This would be a cyclone from years past. You can see your cyclone centered over here at 850 millibars, which is a level that we will commonly look at for temperature advection, helping to remove some of those influences we see down at the surface. And so you can see the center of our low pressure would be located over eastern Kansas, and we see our rotation in the wind barbs, and we see some cold air here spilling in behind your cyclone, and we can see out ahead of this some warmer air pushing northward ahead of our mid-latitude cyclone. And so I encourage you to take a quick pause. I will break for about 5 to 10 seconds and consider where on this map we may have temperature advection, either warm or cold. Okay, you had a chance to stop the video, give a little look at this and see how things might be going. When we're talking again about advection, we need to really consider local areas in which we're seeing a change in temperature that is influenced by our horizontal wind. And so one area that likely stuck out to you would be this area across Texas. The wind is helping to blow colder air into areas that were just recently much warmer. And so what would we expect the temperature to do around Dallas in the next hour or two? More than likely get colder. Conversely, if we work our way out to the plains, we can look maybe even over northern Indiana. Let's consider Valparaiso. The winds are blowing with at least some component that would suggest a warm air advection scenario. Consider other areas, however, say the Arrowhead of Minnesota. We still have wind. We still have the motion of temperature, or I should say temperature being moved around by the wind, these different air masses, but in many ways our temperature is similar across the area, and so we would have minimal temperature advection in areas such as northern Minnesota. And so we can look here at a computer-derived version of temperature advection. And so again, you can see the areas here across Texas where we have cold air moving in. We have some pretty good regions of cold air advection. Areas in Indiana, Illinois, not too far away from our 850 millibar warm front, again experiencing some form of warm air advection. And then again over Minnesota, pretty minimal in terms of advection. So I toggle back and forth. One more time. And so I encourage you to look a little bit more at these different types of advection, take a look at some vorticity maps, and continue to gain familiarity with how this works in the atmosphere, understanding why as meteorologists we are interested in learning more about these parameters in the atmosphere. That's all for this video. We'll talk more about these in a real-time weather discussion sense in the subsequent video, and then we'll talk a little bit about the tasks in your handout and what we challenge you to do to help understand this meteorology better as you work on these videos from home. Thank you very much. Take care. Talk to you again soon.